Everybody, this is Jono from Seneca, and in this A-level chemistry revision episode, I am going to be talking about how to increase rates. We're going to get fast. Scream if you want to go faster. Great Jerry Halliwell song, circa 2000, before things went a little bit downhill. Check it out, make a connection. It will help you remember what we're about to go over. If you are new to this series, make sure you check out some of the earlier episodes because we are going to be building on a lot of the knowledge previously covered. So without further ado, let's get involved into increasing rates. So changing reaction rates. There are many chemical reactions that we would like to go faster, such as the Haber process. That's going to be coming up soon, so get excited. And many that we would like to slow down, like explosions. The main methods for changing reaction rates are changing temperature. We saw the effects of heating on the Maxwell-Boltzmann distribution of energies. If that doesn't sound familiar, make sure you check out the episode on Maxwell-Boltzmann distributions. And a little sneak peek if you haven't listened to that episode yet. It raises the average energy but lowers the peak of the graph if we increase the temperature. So increasing the temperature gives the molecules more energy. So there are more molecules that have an energy that's greater or equal to the activation energy. This means there are more collisions that will have the energy to react, so the rate increases. Heating the mixture also increases the number of collisions in total, so heating increases the rate through two pathways. One, there are more collisions. Two, there are more successful collisions, so the rate is going to shoot on up if we increase the temperature. We can also change the concentration. In solution, the majority of the collisions a solute particle experiences will be with water. We want more of these collisions to be with the other reactant, as the rate will increase. By increasing the concentration of the solution, we increase the number of collisions that happen between reactants. This means that there will be more successful collisions, hence the rate will increase. Changing the pressure. In a gas, the molecules are far apart, and we can consider this thinking about the ideal gas law, which is PV equals nRT. If we increase the pressure, we reduce the volume of the gas. This means the molecules are closer together. If the molecules are closer together, they will collide more often. Think of it as like being on a tube platform in rush hour. The closer everyone is, the more you bump into people. That's a nice little simile, isn't it? This means that there are more successful collisions and the rate will increase. Catalysis. A catalyst helps to increase the reaction rates by offering an alternative reaction pathway. The rate is higher because the new pathway has a lower activation energy. So a greater proportion of molecules will have energy greater than the activation energy. This means that there will be more successful collisions. So that is catalysis. So if we increase the rate by increasing the concentration, it means that we increase the number of reactant molecules with respect to the number of solvent or water molecules. So that was just a nice little review about how increasing the concentration of reactants means that there are more reactants with respect to water molecules. So there's going to be more successful collisions. Let's go into the theory behind increasing pressure again. Let's think about that ideal gas law. PV equals nRT. So if we increase the pressure, we're going to reduce the volume of the gas. This means the molecules are closer together, so they will collide more frequently. So the theory behind increasing pressure all relies on that nice little ideal gas law, PV equals nRT. Increasing the pressure, we reduce the volume. Let's go over some diagrams to explain catalysis. Enthalpy profile diagrams and the Maxwell-Boltzmann distribution can be used to explain how catalysts work. Enthalpy profile. So on an enthalpy profile, the catalytic pathway will have a lower hump, and the hump represents the activation energy. This is because the catalytic pathway has a lower activation energy. So on an enthalpy profile diagram, we can represent a lower activation energy by drawing a smaller hump. On a Maxwell-Boltzmann graph, we can see that if we add a catalytic pathway, more molecules have enough energy to react via the catalyzed pathway. And that is because more molecules will be able to reach the activation energy, because with the Catalyst deactivation energy is lower, so more molecules will have the required energy to react. So next we're going to go over some facts for catalyzed reactions. Which of the following is not true for catalyzed reactions? They have a greater rate of reaction. They have more successful collisions. They have a lower activation energy. They have fewer collisions. Which one's not true? It's the last one. They don't have fewer collisions. That's not true for catalyzed reactions. All the other points were true. They have a lower activation energy, there are more successful collisions, and there's a greater rate of reaction. So that just about brings us to the end of this episode on increasing the rates of reactions. I hope that was a useful run through. Make sure you check out the other episodes in the series so you get fully up to speed on kinetics and enthalpy and temperature changes and all that fun stuff you need to know for your A-level exam. I've been Jono, thanks for joining me, and hope to catch you in the next episode.